Hi, today we are going to create another project. So we will design it in VHDL and then we will implement it on FPGA board as well. So in today's project, we will drive a pattern on a set of 4 LEDs. These 4 LEDs will be connected with the FPGA board and at the initial stage, only first LED is on and rest 3 LEDs are off. We will also use one switch button in this project as an input. So when I press this button on the development board, then this LED pattern will shift one by one at each press of switch like this. So at initial stage, first LED is on, right? And rest 3 LEDs are off. Now I press the button, then second LED will on and other 3 LEDs will be off. Now I press the button again. Now third LED will on and rest LEDs will be off. Now I press the button for the third time, then this fourth LED will on and rest LEDs will be off. Now if I press the button again, then again the first LED will on and rest 3 LEDs will be off. So this pattern will run in a cycle and we are basically shifting our output when we press the switch input, right? So this is a kind of shift register. But we will see that how to implement this in FPGA. We will also have a reset switch as well. And when we press it, then we should jump to the initial stage. Means first LED is on and rest 3 LEDs are off. In this session, we will also talk about the bouncing problem in a switch. So let's move to the Quartus Prime software and start developing it. But a quick brief that what and how we will design this. So first we will design a 4-stage shift register which will shift the LED output when the button is pressed. So we will have something this kind of a structure. We will need 4 registers and state of each register will be connected to the each LED output. So to create that LED pattern, we need to connect these registers in a series like this. Means output of one flip-flop will go to the input of next flip-flop. Like output of first flip-flop going to the input of second flip-flop. Then output of second flip-flop going to the input of third flip-flop. Then output of third flip-flop going to the input of fourth flip-flop. And finally output of fourth flip-flop again going to the input of first flip-flop. So it is in the loop. And then we will connect each LED to the output of each flip-flop like this. So what will happen that we will reset these register output to 1000. Means first LED is on and all the other LEDs are off. And then for each press, this data will shift to the right. Like when you press the switch, you will get 0100. Means now second LED will on and rest LEDs will be off. And for the next press, this data will be 0010. Means now the third LED will on and rest will be off. Now remember that we want our LED pattern to shift only when the button is pressed. Means we do not want to shift this data all the time at our clock cycle. So we only want to shift data when button is pressed, right? So we need a shift enable input like this, which will control this shifting of data, right? Means when this switch press is detected, then only your LED pattern should shift. So we need to think about this functionality as well. Now because this switch is a asynchronous in nature, so we will convert it into synchronous signal by using two-stage flip-flop like we discussed in the best practice sessions. And third, we will write another process to detect if the switch is pressed or not. Now this is very important because you are designing your system with a 50 megahertz of clock frequency. So if you use this to shift your LED output, then it will happen at very high speed. And you will not be able to see any shift with your eyes because that will happen at millions of times in a second. So we has to do something for it. So we will drive one extra internal signal to bypass this problem. Means your LED will shift only when switch is pressed, not at every clock cycle. So this will be interesting to see. So let's move to the practical. Okay, so we will start our quarter software. So write quarters, and we are having this quarters 2 10.1 web edition. So we will open this one because we have device Cyclone 2 and that is not supported by the newer version like we have installed in our machines. So we are using this quarters 2 software that is 10.1 version. Now this is our landing page. So first we will create a new project, and for that we have this new project wizard button. So click on it. Okay. Now click on next. Now give some folder name. So suppose I'm giving project 01 and give the project name. So my project name is project 01, for example. Now click on next. Click on next. Now we will select our device. So I have Cyclone 2. So I will select it. Package. I have this one. 208 pins I have, and grade is 8. So there are 4 devices and I have to choose my device name. So I have this one, AP2C5Q208C8. You will select whatever device you have for your working. I have selected it and now click on next. Although I am not doing the simulation, but you can choose whatever simulation you are using. So it's the same. Now click on next and now click on finish. So the project has been created. So we have this project. Now we will open a new file, or we will create a new file. So I will create on this button, or you can go from here as well. So file, new. So both are doing the same job. And now we will select this VHDL file because we are writing our code in VHDL language, right? So select VHDL. Now click on OK. So this has been opened. So this is our programming editor. Okay, so we will write a program here. So library IEEE use IEEE.std underscore logic underscore 1164 dot all. Now define the entity. So write entity project 01 is port. Now you will define your ports here. So what we have clock as an input. This is std underscore logic type. We have reset in std underscore logic type. We have switch SW in std underscore logic type, and we have output. So suppose output is LED and this is out, and we have 4 LEDs, right? So instead defining 4 separate signals here or 4 separate ports here, I will choose this std underscore logic underscore vector signal. So this is 1 to 4. So each individual element is treated like a single LED as an output. Okay. Now everything has been defined as an port, input output ports. So we have these 3 inputs and 1 single output, but this is vector type. Okay. Now I have defined all the ports, then bracket close, semicolon, and entity. So and project 0. Now it's time for architecture declaration. Okay. So we are defining our program here. We are defining our functioning here. So architecture behave of project 01 is now begin, and in the last and behave. I'm just writing the structure first. Okay. So first we will design our shift register like I explained, right? So for this we will write a process block. Okay. So we will defining some process name. So this is suppose shift process. Now this is the registered process block. So we will have clock and reset in the sensitivity list, right? Now begin and end process. Now because this is register process block, so definitely we will have reset and clock. So define that body. If reset equals to 0, then now else if rising edge of clock, then end if. So this is our general body for registered process block, right? Now we will define our functioning here. Now, if you wonder why reset is equals to 0, because we are using a physical switch, right? And our switch is by default set to 1. And when we press it, then it is asserted as logical low or 0 value. So by default, when it is not pressed, it is having the value of 1. And when we will press it, then we will get 0. So when it is 0, it is asserted. Okay, so that's why it reset is equals to 0. Okay, so don't confuse why reset is not equals to 1. Okay, so if reset is equals to 0, now what we want our shift register to set to the reset value, right? So for this we are needing a signal, antenna signal. So define that signal. Suppose this is shift register, and this is again std logic vector, and it is having the same range like our output. So we have led, so I'm giving led range. Okay, you can initiate some initial value as well. For example, I'm giving 1000. Okay, so if reset is equals to 0, then our shift register will set to default state. Okay, so shift register will get the value of 1000. So this is our default state. Then if you wonder that why 1000, not something else, not 4 times 0, so it comes from our requirement. So what we have said that we have one LED that is on and rest of the three LEDs are off, right? So this is our LED 1 that is on, and we have rest three LEDs, these are off. Okay, so that's why it is 1000 for the reset condition, right? Now what will happen at the rising edge of clock? So if switch is pressed, so suppose give some name, suppose I'm saying button pressed. If button pressed is equals to 1, then we need to shift our registers, right? We need to shift our data into the register, right? So we will have shift register 1 will get the value of shift register 4, right? So it is moved from last to first LED. Okay, same shift register 2 get the value of shift register 1, right? Now shift register 3 will get the value of shift register 2. Again shift register 4 will get the value of shift register 3. So we have 4 states of shift register, right? So I have written 4 statements here. This is fine at the moment because we have just 4 registers. Now suppose if you have 100 of registers from which you are shifting your data, then you need to write 100 of lines here, right? And that is impractical. Okay, so I've explained you one simple way of doing this. So what it is, so we can write that shift register gets the value of shift register 4 concatenation with shift register 1 to 3, right? So if you break down this statement, then it will be like shift register gets a value of concatenation with shift register 3 concatenation with shift register 2 and concatenation with shift register 1. So this statement and these statements are equivalent. They are exactly same, right? Now, if you split this shift register again, so suppose you are splitting this shift register, so it will be shift register 1 concatenation with shift register 2 concatenation with shift register 3 concatenation with shift register 4. So for this shift registers having 4 elements. So these are the combination of shift register 1, 2, 3 and 4, right? So all of these 3 statements, like this statement and this statements are exactly same. Okay, these are just representation, different representation. Okay, so this is the statement which we will use. Okay, so I will remove these two statements here, and we will only use this single statement. We don't need these four statements because this statement will do the same job. Okay, so if button is pressed, then shift register will shift one data at each clock cycle. Okay, so this is the me. Now close this, and if, so we have terminated this if condition as well. We have terminated this if condition, and we have terminated this process block as well. Now we have used this signal named as button pressed, but we have not defined it, right? So first we will define this. So this is a signal button pressed. This is std underscore logic type. Now we have defined this, we have used this, but we didn't tell that how we will get this signal, right? How it will be operated. Okay, so next process we will write for this button pressed. So we will need another process. Now, before doing this, we have important thing to do, and that is synchronizing this switch. Okay, we have this input switch, and that is asynchronous in nature. Means we can press that switch at any point of time. And remember, I have explained that we should synchronize all of our asynchronous signals, right? So this is asynchronous. So we need to synchronize it. How? Well, by two flip-flop chain, right? So create a new process. So suppose we are giving this some name like process underscore sync. Okay. Now this is a process. Again, this is a register process block. So we will have clock and reset in the sensitivity list. Now begin and end process. So we have just created the body for this one. Now default structure, if reset equals to 1, then else if rising edge of clock, then and if. Okay, so this is our basic structure. Now for this sync process, I will create another signal. So suppose we are creating a signal. So what I have said, we are using two flip-flops in a chain, right? So we are needing two internal signals. So I'm creating one single name. So signal sync, that is std underscore logic underscore vector 1 down to 0. Now it is having two elements, right? Now coming here, if reset is equals to 1, then this sync signal should be 1 1. Okay. Now else if at the rising edge of clock, then sync 0 gets the value of switch. So this is the input switch, right? This one. Okay, so this is our input. And then this is one stage of flip-flop. So at the first rising edge or first clock cycle, this switch input will go to this sync 0. So this is one stage. Now for the second stage, sync 1 will get the value of sync 0. Now you can say that we are moving switch input to the sync 0. Then we are moving sync 0 to sync 1. So it is the same thing, right? But no. At the first rising edge clock, this switch input will go to the sync 0 signal. And then for the next rising edge, sync 0 will move to the sync 1. So from pressing this switch to this sync 1, you will need 2 clock cycles. So that's what it is doing. Okay. And now this switch input, which is a asynchronous signal, now this sync 1 is a synchronized signal. So this sync 1 signal, that is a synchronized version of this asynchronous input, that is switch. Okay. So whenever we are using switch, we will use instead sync 1. Okay. So that it is what it is doing. Now terminate this if condition and end process. So we have this single if condition. So we have terminated it, and this is our process section. Okay. Now we need to detect the press button when your switch is pressed, right? And for that, we will again write another process. Okay. So this is process for button triggered or button detect. Okay, now this is process. Again, this is a registered process block. So we will use clock and reset in the sensitivity list, then begin and end process. Now again, this is registered process block, right? So just write the basic structure of it. If reset is equals to 0, then else if rising edge of clock, then end if. Well, we have used this reset is equals to 1 by default. Uh, so we will correct it. So this is reset is equals to 0, reset is equals to 0, reset is equals to 0. Okay. So now everything is good. Now we need to create some more signals, right? So this is a delayed version of input switch, right? So we will create one another signal for that. So this is signal delayed switch. Okay. And this is again std underscore logic. So when reset is equals to 0 or when reset is applied, then this delay switch, so this delay switch will get the value of 1, right? Okay. Now else if at rising edge of clock, then if sync1 is equals to 0, means when the switch is pressed. So you can treat it just like our input switch. Okay, like this one, right? But what it is doing, it is the synchronized version of your input signal. Okay, so we are using this sync1 instead of a asynchronous input, that is switch. So this is same. Okay, just we are using the registered version. Okay, or synchronized version. So sync1 is equals to 0, and what we are needing a falling edge of our signal. Means when it was not pressed, so you will have the value of 1, and when you will press it, then your value will be 0. So you are needing a falling edge of your signal. Now, if you do not do, then remember what is your clock frequency? That is 50 megahertz. And at this 50 megahertz cycle, your register will shift your data. Means this is 1000, then 0100, then 0010, and that will happen at every rising edge of your clock cycle at 50 megahertz, right? And that is not our requirement, right? Because what we want that when we press our switch, then only the shifting will be applied. And when we are not pressing our switch, then nothing will happen, right? So we are needing this condition. So sync1 is equals to 0 and delay switch. Yeah, so the spelling is correct. I'm just checking. Okay, so this delay switch is equals to 1. Then now why this one? So we are saying that our switch should be pressed, means this should be value 0, and delay switch is equals to 1. Now why delay switch is equals to 1? So we need to define it first. So let's define it. So we will define it here. So delay switch gets the value of sync 1, right? So you can say that delay switch is getting the value of sync 1, and now I am checking this sync 1 is equals to 0 and delay switch is equals to 1. That is because this sync 1 is one cycle ahead of this delay switch. Means your delay switch is one cycle backward than the sync 1. So that will detect your falling edge of your switch. Means when you press your switch, then your signal will go from 1 to 0. And that's what we are detecting, right? So this is the statement. So if sync 1 is equals to 0 and delay switch is equals to 1, then what will happen? So we have this button press signal, which is driving your shift register, right? So we need this button pressed signal to be 1. Okay. So we are using this condition, right? Button press is equals to 1, then do the shifting operation, right? So if this is happening, means when we are pressing the switch and when it is detecting it, then this button pressed will be 1. And if it is not detecting this, then what will happen? This button pressed will be 0, right? And if now it is better if you set this condition at the reset condition as well. So when reset is applied, then delay switch will be 1 and your button pressed is 0, means that is not pressed. Okay, now everything looks good. So this is the one if statement block, and this is the another block. Everything is closed, terminated well, and this is the process that is again terminated well. Okay, so this is our VHDL program. Okay, so everything looks good to me. Now just save this file. So save it as project 01, save. Now let's compile it. Let's see if everything is good or it is having some error. So there are a lot of error, I think. Okay, so okay, we missed to terminate well this entity. Now save, again compile. Okay, perfect. So everything is good. Okay, so everything is good and we have successfully compiled our VHDL program as well, and there is no syntax error. And logical, this is looks good. Okay, now what is the next step? The next step is pin planner. Okay, so at this step, we will define our input outputs and we will tell that these input outputs are connected to which pin of our FPGA. So this is our FPGA board. Okay, this is Cyclone 2. This device we have selected, and this has 208 number of pins. So you see these different colors. So this is A side, this is B, this is C, and this is D. Okay, so we will define our input output signals to these FPGA pins. So we have this clock signal, and in our board, this is connected to pin number 23. Okay, now these are our outputs: LED1, LED2, LED3, and LED4. And now these are connected to 15 pin. Now next LED is connected to 13 pin. Next one is connected to 11th pin, and the fourth LED is connected to the pin number 8. Now reset is connected to the pin number 28, and switch is connected to the pin number 27. So I have mentioned that which signal or which input output port connected to which pin of a physical FPGA, right? Now close this window. Okay, before going further, let me tell you one important thing. Now, because what is happening, we are pressing a switch and that is being detected that when you are pressing your switch, then your signal goes from logical high to logical low, right? But a switch is a physical key, right? And that is having the mechanical system inside, okay? And that is not very smooth. So sometime it can happen that when you press your button, then internally it will give multiple pulses, okay? That we generally called bouncing of switch. So what will happen that if you press your switch, then instead having a single pulse, it can have multiple pulses. So in that case, your shift register will shift your data multiple times. Means it is possible that at some point of time, LED 1 is glowing, and when you press a switch, then LED third is glowing. It's jump from 1 to 3. It means that it is getting two pulses in between, and that is super fast because you are working on a 50 megahertz clock frequency, right? And that is very high frequency. So bouncing is a problem in a switch. So as a solution, we need to debounce that switching, and we will do that in the next session after understanding the concept that what are the reason for the bouncing a switch, a physical switch, and how to debounce that. Okay, so we will understand that logic first and then we will implement it. But for now, just implement this program. Okay, so what we have did, we have written our VHDL code, then we did the pin planner, means we assigned our input output ports to a physical pin. We mapped these things. Okay, and now it's time to program our device. So we will open the programmer from here. Now select our file and we have this start option flashing here. Now just click on it and boom, your FPGA is programmed now. Okay, so now let's see that how this program is actually working on the real life hardware system or real life FPGA device. So you can see that we are pressing our switch single time, but our LEDs are shifting more than once. And that is because switch bouncing problem, which we were discussing about. And we will solve this in the next session. Okay, so that was our project. This may seem little complex at the moment, but try it with yourself and you will become comfortable by time. We have also observed bouncing problem of switch in this practical. So what was happening that we were pressing our switch at a single time, but we observed multiple shifts. Because of that shift bouncing problem. So we need to solve this problem by debouncing our switch. So we will understand the logic of debouncing in the next session. And then we will apply that in this project. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.